Okay, so today we're looking at problems involving geometric sequences. And the first problem we're going to look at is this one. So we have a sequence and we have 3, 6, 12, 24. This carries on till infinity. And the question is, when does this sequence exceed 1 million? So what is the first term in the sequence that is bigger than 1 million? And that's the question. So to approach this, we need to think about what's defining the sequence. And what we can do is we can write a for the first term, so a equals 3, and then the common ratio, the number that we're multiplying to get between terms is 2. So 3 times 2 is 6, 6 times 2 is 12, so our ratio is 2. And in fact, these two bits of information define the whole sequence. And now the question is, we need a general formula for the nth term in this sequence. And if you remember, this is given by un for the nth term. This equals a times r to the n minus 1. So a is our initial value, and then r is our ratio. And this gives us a formula for the value in the nth slot. So this is the first term, second term, and for the nth term is given by this formula. And we've worked out what a and r are, so we can just sub that in. We have 3 times 2 to the power of n minus 1. So now to solve this question, we just need to think about the inequality. When does un become greater than 1 million, which I'm going to write more conveniently as 10 to the power of 6. So let's just sub this in. If I go over here, 3 times 2 to the power of n minus 1 is greater than 10 to the power of 6. So we need to solve this to get it in terms of n. So I'm going to start off by dividing by 3. 2 to the power of n minus 1 is greater than 10 to the power of 6 over 3. And the sign doesn't change because we're just dividing by a positive number. And now we have this n in the power here, and we want to kind of get it down. So a trick we can use is we can apply the logarithms. So if we apply the logarithms to both sides, this doesn't change the sign. So we have log of 2 to the power of n minus 1, and this is greater than log of this stuff, which is 10 to the power of 6 over 3. And the reason we did that is because we have the power rule for logarithms. So we can bring down this power to the front. So this actually equals n minus 1 times the logarithm of 2. And then we can solve this. We can just divide by log 2. This is positive, and then just add 1 onto both sides, and we get n is greater than log of 10 to the power of 6. 10 to the power of 6 divided by 3. And then this is divided by log 2. Just dividing this number. And then we've also got a minus 1 here, so I just need to add 1 here. And this is a bit messy, but if you plug this into a calculator, this comes out as about 19.35. So what does this tell us? So this gives us a condition for when our term in the sequence is bigger than 1 million. So this isn't an integer, so 19.35 isn't going to appear in our sequence. But what it does tell us is the next number up. So if we take n equals 20, this is greater than 19.5. It's the first integer that is greater than this. And it's equivalent to this inequality, so it tells us that the 20th term in the sequence is greater than 1 million. So, and this tells us it's the first time that the term in the sequence is greater than 1 million. So this is our answer, n equals 20. So now we're looking at the second problem. And this is a bit wordier, so let's just read through it. So we're given these 3 bits of information. First off, we invest an amount, A pounds, or whatever currency you want to use. We invest an amount of A into a bank account at time 1. And then in that bank account, we have an interest rate. And that is given by 4%. Every year, our value increases by 4%. And then after 5 years, we are told that this investment is worth £10,000. And then from this, we need to work out what A is. So let's start off by translating all this word stuff into maths. So this is going to be a geometric sequence. So let's start off by, let's define Wn to be the value at time n. Time n. So the first bit of information, it tells us that W1 equals A. So that's nice and simple. And then looking at the third bit of information, this tells us that after 5 years, our value is 10,000. So we need to be careful about the indices. It's not 5 here, it's actually 6, because our times increase by an amount of 5 years, so we need to add 5 to the index here. So our time at time 6, this is equal to 10,000. That's what this is telling us. And then the second bit of information, interest rate, we just need to know that this is the same as multiplying by 1.04. So our interest rate is 4%, so every year our value increases by a multiplicative factor of 1.04. So this tells us that our ratio between terms in the sequence, the common ratio, is going to be given by 1.04. So now think about how we defined a geometric sequence. We have the ratio, we have its initial value, and we also have a formula for the general nth term in this sequence. So remember that the general nth term, this is given by the initial term, which is a, times the common ratio to the power of n minus 1. So from this, the idea is we want to work out what a is. And to do that, we can actually equate this equation at time 6 because we know its value. So if we just plug in n equals 6 into this formula, we have a times r to the power of 5. And we see now why we use 6 here, because after 5 years, the amount has increased by 4% 5 times. So this is equal to 10,000. That's what we were told, 10,000. And now we know what r is, so we can just divide by this and we can find what a is. So this is kind of the idea to this question. So just dividing by r to the power of 5, and I'll sub it in. So this is 1.04 to the power of 5. And you can plug this into a calculator. This is about £8,219 £8,219 and 27 pence. So this tells us the investment we need to make at time 1, so that after 5 years, this investment is now worth £10,000. So if we put £8,219 in the bank, we're going to be left with 10,000. So this is a really nice problem because all over the finance sector, a lot of compound interest models is just geometric sequence. So it's really important to understand them. So I've got one more question that we're going to look at. I'm just going to clear the board. Okay, so now looking at the final question of this video, and this is about decay problems. So we're told that the value of a car, this depreciates by 15% a year. So this makes sense because when you typically buy a car, the value is going to go down over time because you've used it. And then we're also told that after 3 years, the car is now worth about £11,000. So £11,000, 54 pounds and 25 cents, pence, whatever unit of money you want to use. So these are the two bits of information we're told. We need to translate this into geometric sequences so that we can answer this question, which is to work out its price at the time you bought it, and also the value after 10 years. So let's start off by defining a geometric sequence. So we can let the first term in the sequence, u1, to be equal to a. And if we can find out what a is, this is going to be the first part of the question. And then thinking about this bit of information, it's going to depreciate by 15% a year. This tells us what our common ratio is going to be. It actually tells us that our common ratio is going to be 0.85. And this is because it's essentially 1 minus 0.15. So our value is going down, so we're multiplying by a number that's smaller than 1, and we're essentially removing the value by 15%. That's why we have 0.85 as our ratio. And so our second terms are going to be a times r, and etc. And then the nth term, as you know, it's given by a times r to the power of n minus 1. So this is good because we know what r is, and to find out a, we can just evaluate at the point after 3 years. And then we can work out what a is from that, just from working backwards. So we need to be careful because we don't want to find the third term in the sequence, you need to find the fourth term. And the reason behind that is similar to the last question, is because 3 years have passed, so we need to add 3 to the index. So you'll see why it's a bit clearer if I write this. We have a times r to the power of 3. So we've applied the depreciation ratio 3 times. That's why we need the index of 4 here. And then we're told from the question that this value is equal to exactly 11,054.25. And since we know what r is, it's kind of a similar problem. We can work out what a is. So a is given by this divided by this. So 11,054.25 divided by 0.85 cubed. And very, very conveniently, this comes out to be £18,000 exactly. So that's just because the question was constructed like this. So this tells us that the initial price of this car was £18,000. And after 3 years, it's gone down by quite a lot. It's 11,000. So this is kind of how we got to this. And then we've also got the second part of this question. So we need to find the value after 10 years. And that's just essentially plugging into this formula. Now we've got A and R, we can actually evaluate the worth at any point in time. And to work out the value at 10 years, we need to work out the 11th term. So we need to find U11. And again, this is because 10 years have passed, so we need to add 10 to the index. So U11 is given by A times R to the power of 10. And we can just plug that in. This is 18,000 times R, which is 0.85, to the power of 10. And if you plug that into a calculator, this is roughly £3,543 and 74 pence. So after 10 years, the car is going to be worth about £3,500. And you see that's very quickly decreased. So the value has dropped very quickly. And this is kind of always true in a geometric sequence. It's going to grow very quickly or decay very quickly. So we've worked out the initial price and the value after 10 years.